Hello, everyone, and thanks to participate to this school. And what I will try to do in this 30 minutes, more or less, lecture is to give you an idea of what is the spectral data and why we use it and which information we can have it. And in particular, we will focus on reflectance spectral data. So you have already seen something before from Ricardo, but just to recall it, we generally use remote sensing also to have composition information. That is possible because we are going to acquire images often with the technique that permits to have multiple wavelengths in our dataset. That is like to acquire several images with different filters. This data comes from two, we can say, different typical instrumentation that permit to have multispectral information. That means few wavelength information on a specific range of wavelength, or a higher number of spectral information, so wavelength acquisition on the same spectral range. Often the differences is also related to the fact that having less wavelength permit to have a higher spatial resolution with respect to same images acquired with an hyperspectral sensor. And this is due to even a correlation done with the data volume. But both of them are information that can permit to retrieve some compositional indication from the surface. Apart, in general, this information can be acquired considering directly information more related with the mineral phases or with the elements that are present on the material in the first microns or centimeters on the surface. Generally, we have to consider two different spectral range, one closer to the visible and the infrared that permit to have information related to the electronic or molecular absorption that permit to analyze mineral phases that have specific absorption, or the opportunity to have information about the elements present in a range that is correlated with the gamma ray and X-ray wavelength range. And this permits to have information about the presence of iron, titanium, or several other elements on the surface, not directly related with their mineralogical information. Often, the information that permits to be acquired with a higher resolution, so closer to the mapping resolution, is related to the mineralogical information, and so to the visible to the near infrared spectral range. And this is much more what we are going to see later on this presentation. And in general, we speak about spectroscopy. That is a technique that permits the investigation of a sort of the material thanks to the interaction between an energy and that matter. So we know that we have a general radiation, that is the electromagnetic radiation, that is the dynamic energy that permits to be used easily because is present thanks to the presence of the sun. So we can use this energy to understand the matter that interact with it. This energy is you can say in a dualistic model, and it permits to explain the nature of the electromagnetic radiation, considering the wave theory of Maxwell and the quantum theory of Planck. We are not going to enter in details about that. We have just to remember that this permits to have an energy transfer, and this is what we use then to have information from the surface. So recalling what is important is that we have a radiation, and we have the interaction between this radiation and a surface that is characterized by some material. And generally, in the range where we can study the minerals present on the surface, we have two different kinds of transition that can be considered to have this important knowledge, that are electronic transition, that is generally related to the presence of transitional metal that have an incomplete orbital present in the structure, and this permit, if there is enough energy, to have some jump of electron to an higher quantum energetic level. And this we'll see later on what means. Or molecular transition, that is much more related to alteration of the electronic orbital energy states. And this is due to the fact that if the material receives this energy, there will be some vibration that of an atom with respect to another, and this permit to have a variegation in the spectral features. In particular, if we consider the electronic process, we can clearly see that there is a wide range of effects that can be present on the material. Often of them are related to the fact that an energy interacts with the surface, and if this material have the opportunity to have a quantum jump of the electrons present in some elements, like for instance iron, we can clearly see a different wavelength if there is no interaction, if there is absorptions, or if there is emittance or other properties of the material. And studying those properties, we can clearly evidence which kind of phases we have on the surface. Reducing to the aspect that mainly we study them from remote sensing, that is information from reflectance or emittance, and summarizing them, we can clearly see that the interaction between the electromagnetic radiation and the matters permit to have from an incident light the three different kind of principal effect. That is, the light can be transmitted, and so we have no information on the light because there is no change on our atoms. We can have a reflection, and so we have a change of the light in the direction of the light that kick the surface, or we can have an absorption. This permits to have a change of the energetic level of an electrons, and this means that the light or the energy is not coming back to our sensor. The other aspect that we can have is the emission of the material that can be seen and can permit to have information of the material that is present on the surface. And this generally is due to the fact that the energy that keep the surface is partially absorbed and re-emitted later on from this material. In some cases, like for radiative material, we can have an emission without any stimulation. This is we can say generally used from remote sensing information, and so from the missions to have information, because it's a sort of easy goal. We can say that spectroscopy, reference spectroscopy, is a passive remote sensing technique, because we have the sun that is illuminating the surfaces, so is sending its energy against the surfaces of the bodies that we are studying. And so thanks to that, we can both study reflectance spectroscopy considering the incident solar radiation, but even the emission at longer wavelength of the surfaces. And these two kind of information can permit to have a higher detail of the mineralogy present on a surface. In particular, entering much more in detail about the reflectance, that is the technique where we have an higher number of data sets for the different bodies that are studying the planetary surfaces. We have just to record that is the study of the light that is reflected or diffused, or if you want, scattered from a body as a function of the wavelength. And this is an important point because the wavelength variation means that at different wavelengths, the same material will behave differently once it's illuminated. And so if, for instance, we have a light that illuminates specific minerals, we'll have a fingerprint of these minerals. And so you can see in the plot in the top right, a specific spectra of an olivine, for instance, and you can clearly see that the reflectance is different for this material at a different wavelength. And this is what permit us to have an information of this material, because this variation, wavelength to wavelength, change from mineral to mineral, from transitional element to transitional elements, or from molecular absorption to molecular absorptions. And so different crystal structure or different elements present in the crystal structures permit to have a different fingerprint, and so recognize different materials. And in particular, what's play an important role is those wavelengths where we have a less reflection of the light that are generally called absorptions. And these absorptions permit us to have information on the surface. In the other say, I was telling you that also emittance can be used, because emittance is the energy radiated by a surface of a body per second per unit area, and in particular the emissivity that related the differences between the radiation emitted from a surface with respect to a black body. So we can say a standard that we know at the same temperature permit to have information in a different range in general. So at longer wavelength with respect to the reflectance, but still correlated with a different characteristic of the minerals. This information is often complementary to the other one, because it's much more related with the asymmetric and symmetric stretches on the crystal site of different minerals. So we have information of different type of silicate, carbonate, and sulfate, but due to the different process with respect to the information that we have from the reflectance, and in particular the reflectance in the visible to near infrared. This is partially less used because not all the bodies that we are studying permit or have data set in this spectral range. So for this, we are much more focusing here on the visible to near infrared. The data set that generally we use to have this information is called often data cube, because permit to have a neat three-dimension information of the surface in a different way with respect to what you can see from a DTM and so on. Here, the third dimension is related to the reflectance properties and so related to the composition of the material. So this means that in X and Y, you have your image, and for each pixel in the third dimension, you have the information at the different wavelength that we acquired. This data is, we can say, has to be remembered also that this data can be affected by the condition illumination and the different condition of the surface. And so the data that we acquire has to be corrected by the incidence angle and the emission angle. So the angle that the sun and the light from the sun arrive to the surfaces, and the angle that have the instrument with respect to the same point at the moment of the acquisition. But even better, this can be done if we consider the topography of the surface at the best resolution that we can have to correct for their true geometry. So not only the one related to the position of the sun and the instrument, but due to the different surfaces. Another important aspect to remember is that the atmospheres play an important role, because can be transparent or not to the light until to the surface. So for some bodies, it's impossible to arrive to a surface like for Venus, or is very complete and very for small windows, we can have a data set from that surface. For other, like Mars, we have any way to correct the information at the different wavelength to be sure that what we are seeing is the surface and not the effect related to the atmosphere that can have absorption closer or superimposed to the one related to some mineral phases. Just briefly, often the instrumentation are more or less, we can say, built in this way with a mirror that permit to have to translate the signal that is arriving from the surface within our instrument. And then some dispersing element or optics permit to send the information to the detector and to scorporate the different wavelength to permit to have information from that pixel that we are looking for all the different wavelength. This instrumentation often works in two main modes, so push broom mode or whisk broom mode. And this permit to have, in the first case, a line of the image that moving the instrument with respect to the surface permit to acquire several lines, and so to build an XY information. Whereas for each of the line, the second dimension is the wavelength dispersion. So we have for each line is substantially for the samples each pixel of the surface, and for the line each wavelength. Whereas whisk broom mode permit to acquire this information scanning the surface, and so we'll have for we can say acquisition pixel by pixel in this way. And so we have reconstructed the images in a more complicated way because we have not each time an acquisition of a complete line. So once we have this kind of data set acquired, what we can have is information of the composition of the surface, as already anticipated and said before. And this, we are going to see much higher detail now for the visible to near infrared spectral range. And in particular, we can say concentrating in the range that is up to 2,500 nanometer or 2.5 micron. And this because this range is the one that is much more studied for in the planetary science. It's true that this range can be extended up to 5 micron or 5,000 nanometer, in particular where we are looking for ICIS material and salt or carbonate mixed with ICIS material, but often for the inner solar system bodies, so those that you are going to see in this course, we are much more concentrated in this spectral range. As already anticipated, in this spectral range, we have two different kind of information that we can acquire, and this is related to electronic absorption or molecular absorptions. For the electronic absorption, we have generally working, as already anticipated, with the transitional elements that can have, in particular, crystal field transition, but even other type of transition that permit to have absorption related to the presence of transitional elements in the crystal lattice. And on the other side, we can have those that are called vibrational absorptions, or in general, overtones or combination of the overtones that permit to have information related to the presence of water in silicates or sulfates, or the presence of carbonates. We have also to remember that the reflectance spectra are not controlled by only the chemistry of the material on the surface, but even by the type of crystals, their dimension, or the grain size of the particulate material on the regolith, the presence of different type of opacity on the surface of the material, and also depending on the, we can say, the roughness of the surfaces. So for instance, if we have strong roughness, we can even have effect due to the, not only due to the composition of the surface, but for some portion of the images, we could not have information at all because the light cannot be reflected. Generally, what we see to study this material is consider, as say at the beginning, the fingerprint that are generally called absorptions. Each absorptions permit to have specific information, and this information can be summarized considering the band position, and in particular the band minimum or band center after a remotion of the continuum of the spectra that is related with the energy, and so is an information related with the ions present in specific site of coordination site. So for instance, iron 2+, if it's absorbing in a tetrahedral or octahedral condition, will have absorption at different wavelength and with different shapes. Another important information is the depth of the absorptions that is related with the intensity, and so with the probability that that absorption occurs at that specific wavelength. This is important because permit to differentiate some material to the other, or due to different grain size, or due to the different abundance of an absorbing mineral in that pixel. So if, for instance, we have two different minerals in our pixel that are characterized the spectral signatures, and one of them is absorbing at one wavelength where the other is not absorbing, higher is the abundance of the absorber minerals, higher is the depth of these absorptions. Another aspect is the bandwidth that is much more related with the variation of the geometry site. And so, for instance, variation of temperature or pressure on the specific material. These are, for instance, specific mafic mineralogy spectra. These are those between the minerals that are much more studied and easily to see in the Moon, Mars, as well as Mercury, and where they have iron 2+ in their site, in their crystal lattice, they will have absorption that are strongly diagnostics. So you can see for pyroxene, you have two different absorptions closer to 1 micron and 2 micron that are telling us which type of pyroxene is and which type of composition have that pyroxene. Or, for instance, you have the case of the olivine, where you have a wide absorption that is the composite absorption of 3 different specific absorption due to the presence of iron 2+ in the crystal lattice of olivine around 1 micron. You can also have other type of absorption that are diagnostic, that are related to the overtones, and those are generally at longer wavelength, so 1.5, 2, 2.1, 3, 2.5 microns, and they are related to generally hydrated silicates or hydrated sulfates. You can see here a variation of this of some of these minerals like kaolinite, chlorite, that have absorptions in those ranges but a different wavelength, and this is related to different bonding between OH and different metals. For some of them, you can have also crystal field absorption because they have the presence of iron, for instance, in a different geometric condition, and so you have not only the information of the hydration but also the presence of iron in their crystal lattice. Another case, for instance, is the presence of sulfates and different cases of absorption related to that.
5 minutes left.
Okay, so this information, as already said, can be helpful to give information about the mineral composition of the different abundance of a mineral phases. And here you have a case from the lab where you can see different mixtures from a pyroxene and a plagioclase with different abundance, and you can clearly see that it is changing strongly the depth of these minerals, whereas it's changing the position only when we move from dominating plagioclase or a dominating pyroxene absorptions. And this information can be correlated, putting the variegation of band depth of band center with respect to some other compositional parameters. This information can be obtained to separate some band composite band using different modeling. One case is, for instance, the application of a Gaussian modeling that permit to separate where 2 different absorption coexist, the 2 different absorber. Or another approach is to use radiative transfer model that permit knowing the optical properties of different minerals to model mixing of this material. Once we are able to study the spectral properties of a mineral phase or of a mixture, and so we have this capability to enter time to time much more in detail on the different properties of the material that is present on the surfaces, we can even try to understand how to use this spectral information. And generally, two are the principal approach, that is studying the variegation of different parameters. And so simplify in this way the spectral analysis, reduce also the weight of the calculation, and permit to compare between different portion range the spectral properties, or to try to classify the entire data set with some classifier that permit to use the entire data set, and so to have at the end our spectra that permit to describe the properties of a specific area, and analyzing that spectra that is representative of that area, we can discern the information related to the mineralogy. I will give you some example of that. So for instance, here is a case for an hyperspectral classification. The classifier I used was called spectral angle mapper, that permit to describe the spectral variegation of the surface of a planet with respect to some end member that we can give to the classifier. This end member can be extracted directly from the images. And for instance, in these cases, what was done was to, starting from the morphology of different lava flows, and so lava flow that was already separated, to explore the spectral variegation, define a number of different area with different spectral characteristics that was sometimes the same within the same lava flow, or sometimes was different within the same lava flow. So for instance, from these images that permit to have a differentiation of the lavas just in accordance with the morphology, I'm going back to the previous one, we can clearly see that this unit that was quite homogeneous from a morphological point of view have a variegation of spectral properties. So using this kind of approach, we can define spectra that permit to define the variegation of the surfaces, and thanks to this classifier, to evidence where each end member is allocated. And this can be helpful to separate to characterize the lava flow with a specific compositional information. In some cases, a single lava flow is characterized by a single spectra that permit to describe the composition of that lava flow. In other cases, this become multiple that permit to separate in subunits the compositional variegation.
2 minutes left.
Okay, on the other hand, we can clearly use spectral parameters to map on the surface different kind of minerals, and this can be done for different kind of absorption. Here you can see, for instance, some specific absorption related to hydrated minerals, or absorption related to different oxidized iron oxide present on the surface of Mars, of pyroxene, and then this information can be combined to permit to evidence where is dominating a mineral phases, and put this within a map. Just to give you a couple of examples from the Moon and Mercury, here, for instance, is a way to parameterize a spectra from M-cube dataset with the slopes and band depth, and to see how those materials variegated on the surface. So how the information of each single parameters is characterized on the surfaces, and then combine them, for instance, with RGB to evidence different material on the surface. Or the same can be done on Mercury. We are with a multispectral dataset, and you can clearly see that using different spectral range and slope in different spectral range, we can produce and extrapolate information of the material that is present on different area on the Mercury surface. So this is the end. And so I can close here the presentation. I hope to give you an overview of the information that we can extrapolate from spectral reflectance spectra, and how we can use it to analyze the different surfaces.